The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Well, okay. So I thought I would, as last time, before quiz 1 and now before quiz 2, I thought I would just tell you what the topics of the 4 problems are. Remember that trusses are still to be reviewed. And of course, the fun was to find mechanisms, to find solutions to AU equals 0 in the case when the truss was unstable. So you can guess that I'll probably pick unstable truss and ask for mechanisms. Then maybe the key problem for this third of the course is finite elements, that idea, and finite elements we've really only done in one dimension. So, and particularly linear hat function elements. Yeah, I wouldn't be, so I'm not, you see what's not included there is like cubics. I mean, those are really great finite elements, but maybe not so great for an exam. So 1D is enough. Linear elements are enough to do on an exam. And then questions 3 and 4. So this one will be weighted more heavily. Then questions 3 and 4 are the topics that we've been doing the last week, 2 weeks. And I realize we haven't had, full time to digest them, to work a whole lot of exercises. So those will be, right now they're too simple, my questions on those topics, 3 and 4. I'll try to make them a little harder for you, but I might not succeed. So anyway, there we go. So I just felt we can't talk about a course in applied math without dealing with these topics in vector calculus that lead to Laplace's equation. But my heart is really in solving Laplace's equation or Poisson's equation by finite differences, that'll be today, or by finite elements, that'll be Wednesday and probably Friday. Yeah, so this is what this is like the core of the computational side, but we had to do this preparation. And then you know that Peter kindly changed his weekly review session to Tuesday. I think it's Tuesday at noon. You could look on the website. So Peter will be a Tuesday review, and then regular, that's me, on Wednesday. And then the exam, I think, is Wednesday evening. Right. I think, yeah. I mean, just do reviews. Oh, Peter sent me a note about a question on an old exam. I think it was 2005. Question 3, I think it was 2005. Question 3, Peter said he didn't understand at all the solution to 3C. Nor do I. I think somehow, I think there was a little confusion in that, and the answer in there is the answer to a different question. Forget it. I would look at A and B, having looked at this one. I mean, A and B are in the are worth looking at in this div-grad, potential stream function world that we're in. Those are typical exercises in that area. Yes, yeah, questions.
Are the solutions the latest?
Oh, good question. Yeah, thanks for reminding me. So solutions to this homework that you're practicing with, if anybody has typed up solutions or could, we'll post them right away. Yeah. So I'll just hope for an email from somebody who solved some or all of those problems. And of course, you'll see me again Wednesday. Yeah, okay. But that's an invitation for anybody who who worked through those homeworks that I'll never collect, the current homework. Okay, thanks for that reminder. Other questions about the exam, and then you'll have another chance Wednesday to ask about that. So those are the topics. Okay. And before I get to the fast Poisson solvers, there's so much about Laplace's equation to say, and I think it still remains to write Green's formula on the board. And that's sort of the core, the part of the big picture of Laplace's equation is to see this. So we have double integrals now, that's the difference, but we're still integrating AU against W. So AU is the gradient of U, W is W1, W2, and this is now for any U and any W, so I want the inner product of the gradient of U with any W, so this is like the AU-W part. So the gradient of U, that would be a du dx times the W1, and a du dy times W2, dx dy, that would be, so inner products, if I'm in 2 dimensions, inner products are integrals, of course, if I'm dealing with functions. So this is like the AU against W, inner product. AU is those two pieces, W is those, there's the dot product. And now the key idea behind what Green's formula is about, what we used for in 1D, is integration by parts. So an integration by parts is going to produce a double integral in which, so I'm just sort of thinking through Green's formula. Of course, we could just say, okay, remember that formula. But you want to just see it as an integration by parts, see how it evolves. And then we could think. So I plan to do integration by parts. That x derivative will get taken off of U and put onto W1. So I'll have U dW1. Oh, there'll be a minus, right, from the integration by parts. U will multiply minus dW1 dx. So that was this guy integrated by parts. Now this one integrated by parts. A y derivative is coming off of U and onto W2. So that'll leave me with U times dW2 dy with the minus sign. That comes also from that integration by parts. And then there's the boundary term. So there's the term which now the boundary of the region is the curve around it instead of just the 2 points. And what do we see in integration by parts? Well, from the boundary term, we expect a U. And then the key point is it's W dot n ds. It's the normal component of this vector W, because we're looking, well, that's just what it is. So that's Green's formula written out in detail. And this is the formula that tells us that here, if this was A being gradient, this is on the left side, I'm seeing grad U inner product with W. And over here, what am I seeing? I'm seeing the inner product of U with, what's that? If I look at minus, if I have this quantity there that's in parentheses, what's its name? It's the divergence. It's minus the divergence of W. Plus the boundary term. Okay. So this is why I allowed myself this gradient transpose equal minus divergence to see that if A is the gradient, then A transpose will be minus the divergence, and this shows how that, this sort of shows you an integration by, the integration by parts that makes that true. So that's, there's so many, integral formulas in this world of vector calculus, but this is like one to know. And actually, if you want to know, okay, what about the details? Where did that come from? This is actually, turns out to be, and the text will make it clear, is the divergence theorem again. The divergence theorem gives us exactly this. So the divergence theorem applied to the vector field u times w. It turns out if I apply the divergence theorem to that, then I get a whole lot of terms from the divergence of that, and they are these. And then I get this for the boundary, the flux out. Yeah. Okay, so that I just didn't want to leave the subject without writing down the central thing. What does this tell us then? I have a region. In that region, I have Laplace's equation or Poisson's equation. Say Poisson. On the boundary. Now this is the final thing to ask you about. What are suitable boundary conditions for this problem in 2D, right? In 1D, we really, by now, we know boundary conditions, that we know the main ones. There's fixed, where u was given, or there's free, where the slope is given. Now, what do we do here? So this is where we used to be in 1D. That's a straight line. Not perfectly straight, but anyway, straight line. So in 1D, there are only two boundary points. The normal vector goes that way and that way. This is the n in this formula. I think if I just wrote ordinary integration by parts, it would look just the same, and my boundary reduces to 2 points. Here, my boundary is the whole curve around. So what corresponds to fixed boundary conditions and what corresponds to free boundary conditions? So I want to, what corresponds to fixed, or those are the ones that are named after Dirichlet. Other names, or the rest will be free. Those are the ones named after Neumann. And those are what we called natural boundary conditions. So I haven't, just ready to finish this story here. What are the possibilities? Well, in each, we could have part of the boundary could be fixed, part could be free. So fixed would mean, say, some of the boundary, let me call this part of the boundary fixed. So the temperature, for example, is fixed on this part of the boundary. So this would be like, and this might be the whole boundary. It might be fixed on the whole one, but I'm now allowing the possibility that we have here a fixed part, and here we have a free part. In fluids, here we have fixed corresponds to like there's some obstacle there, something, some wall. Free is where the fluid is coming in or flowing out. Yeah, so there it's a velocity condition. Okay, so fixed conditions, these Dirichlet ones will be like, tell me what u is given on this part. So on part of the boundary, or possibly all, I could be given u equal u0. That could be 0. Could be 0, as often was in 1D. We often just took u to be 0. Now, what I'm asking, maybe for the first time, is what's the free boundary condition? What do we prescribe w equals 0 on the free part of the boundary? Is w equals 0 the correct free condition, or w equal w naught if we wanted to allow it to be non-zero? That would sound right? U on one side, w on the other. But now we're in 2D. U is still a scalar. That's fine. But w is now a vector. So if I was to prescribe W on this part of the boundary, I'm giving you two conditions, not one, and that's not good. I can't give you more than one boundary condition, and the clue is there. It's W dot n. It's the flow, the outward flow that you could prescribe. You can't say in advance what the tangential flow should be. So the free condition would be like W dot n, which is, of course, this is the, since W is V, we have Laplace's equation here with C equal to 1 in between W and V. So this is the gradient of U dot n, grad U dot n, and it's sometimes written the derivative of U in the normal direction. And that we can prescribe as some W naught, let's say. Oh, I don't like to say W naught, because W naught makes it sound like it's like a vector would be allowed, and that's the whole point here. We give one boundary condition. We either give U or W dot n. So let me give it some different name like F. Okay. So I'll just ask one more question to bring this home, and then I'll get on to the fun today of fast Poisson solvers. Suppose, what was the deal in 1D when we had free boundary conditions? What was the deal in one dimension when we had free boundary conditions? Both conditions were slope conditions. U prime equals 0. What matrix did we get? What was different about that matrix? The free case. I'm always looking back to 1D because that's the case we really understood. What was the problem with the free matrix? It was singular. What was its name? Was it K? Was it? You remember the first day of class? The unforgettable 4 matrices. So this was fixed. This one was, you could tell me better than I can remember. T was free fixed, and that was still okay. By okay, I mean it was still invertible. What was B? Free. That's what I'm looking at. And the problem with free, and then this was periodic, that's Fourier stuff, that's the next part of the course. But the point is that this free was singular. Right. And it'll be the same here. If the whole boundary is free, then I've got a singular problem. If I've got a whole boundary that's free, yeah, actually, I'll just put it here. Suppose I have Laplace's equation zero, and suppose I make the whole all free. So grad U dot n is 0 on the whole boundary. So I'm solving, it's like solving B U equals 0. And the point is that that has solutions. Do you remember what was in the null space of B, this free case? BU was 0 for what vector? Our favorite guilty vector. It was constants, right, all ones, all constants. U equal 1, all constant. Right, so that was the free case in 1D. Now, I just want you to tell me the same thing over here. That equation does not have a unique solution, so it's a singular problem. Here's the equation, something U equals 0, but you can tell me solutions to that pure Neumann problem that are not 0. So this is a problem where there's a null space. And what is the solution? What's a solution or what's a solution to this? To the Laplace's equation in the inside and the slope condition, slope 0, all around the boundary. There's a simple solution to that one, which is just like this guy. And do you see what it is? U equal constant, right. So U equal constant. So I'd like you to see all the whole picture connecting with what we fully understood in the 1D case for those matrices, that we don't expect to be able to have a pure Neumann problem, a totally free problem, because at least it'll be singular and we'll have to do something special. So the point is that it would be enough for me just to fix that little bit. If I just fix that little bit and prescribed U equal U0 on a little bit, I could make the rest of it free. But I can't make it all free. Right. Okay. So those are things which, just to complete the big picture of Laplace's equation. Okay. Now I'm going to turn to solving it. So now I want to solve Laplace's equation, and then we'll have, because we have the review sessions coming on Tuesday and Wednesday of the past, now we're looking future, forward. Ready to look forward? Laplace's equation on a square. On a square. Okay, so let me draw this square. Laplace's equation or Poisson's equation in a square. Okay, I'm going to make it the boundary conditions. So I'm going to have a mesh. This is going to be finite differences. Finite differences will do fine on a square. As soon as I draw this curved region, I better be thinking about finite elements. So that's Wednesday. Today is the square day. Okay, so square day, I could think of finite differences. I just draw a mesh. Let's make it small. So this is all known. These are all known values. Let me just say U is given. U is given on the boundary. I'll do the Dirichlet problem on boundary. So at all these mesh points, I know U. And I want to find U inside. So I've got 9 unknowns, right? 9 interior mesh points. 3 times 3, 3. So I've got 9 unknowns. I want 9 equations, and I'm thinking here about difference equations. So let me write my equation: minus uxx minus uyy equals some f. Okay. Poisson then. What finite difference? I want to turn this into finite differences. That'll be my 9. That'll be my system of 9 equations. And the unknowns will be the 9 values of U. So these are unknowns, right? Those are the unknowns. Okay, and I need equations. So let me take a typical mesh point like this one. I'm looking for the finite difference approximation to the Laplacian. If you give me Laplace's equation and I say, okay, what's a good finite difference approximation that I can then put in the computer and solve, I'm ready to do it. So what should we do for this one, for that term? What's the totally natural thing to do to replace the finite difference replacement of minus uxx? Second differences. And with the minus sign there, it'll be so second difference is around this point. It'll be a minus 1 of theirs, 2 of those, a minus 1 of those. That second difference in the x direction is my is my replacement, my approximation. And what about in the y direction? Same thing. Second differences, but now vertically. So now I have -1, 2 more. That makes this guy a 4. And this is -1. And on the right-hand side, I'll take the value of f at the center point. Do you see that molecule? Let me highlight the molecule there. 4 in the center, -1's beside it. Our matrix, we're going to produce a KU equal F matrix. And what's the K going to be? It's K2D. Let's give a name, a new name. We've had K forever. Let's have K2D. And U is, so tell me now again, just so we got, what size is K2D for this particular problem? What's the shape of it? How many unknowns have I got in U? 9. 9 unknowns. And notice, of course, near the boundary, you see what's happening? Near the boundary, if this was the, well, let me take the first point. So what does the very first row of K look like if I number nodes like this? So this will be node number 1, 2, 3, 4, 5, 6, 7, 8, 9. So number 1 is sort of close to a boundary. So I have here a -1, a 2, and this is gone. That's like a column of our matrix removed, like a grounded node or whatever. But then I have the vertical one, -1, 2, making this into a 4. And this guy will also be removed. So I think if I look at K2D, it's 9 by 9. I don't plan to write all 81 entries. But I could write the first row. The first row comes from the equation, from the first equation. So the first row has an F1 on the right-hand side, F at this point. And what do you see? What's on the diagonal of K2D? 4. 4. And what's the rest of the row? Well, there's the next point, and it has a -1. And then this point is not connected to that, so it's a 0. I better leave room for 9 by 9 here. 4 -1, 0. Okay, and now what about the rest of the row? So there's 4 is the center, -1, 0, and now I come to here. So what's the next entry in my matrix? -1. We're multiplying the unknown, the fourth unknown. And what about the rest of the row? This guy is not connected to 5, 6, 7, 8, or 9, so now I have 0, 0, 0, 0, 0. Okay. So that would be a row. That would be a row that's sort of different because it's way in the. It corresponds to a mesh point that's way over near the corner. How about the fifth row? What would be the fifth row of K2D corresponding to this guy that's right in the middle? What's on the diagonal? What's the 5, 5 entry of K2D? 4. Good. I'm going to have a diagonal of 4s. I'm going to have 4s all the way down the diagonal. Because every point the molecule is centered at gives me the 4. And I just have a -1 for its neighbors. And this guy has all 4 neighbors. You know, they're all alive and well. So there's a guy. So this is the fifth row. There's somebody right next door on the left, somebody right next door on the right. And then, do the other -1s go after that? This is the whole point. I want you to see how this K2D matrix looks. Because it's the equation we have to solve. So we got to know what this matrix looks like. So what's the point here? 4, it's got a neighbor there. This was unknown number 5. It's 4th unknown and the 6th unknown. But what are the numbers of these unknowns? 2 and 8. So this guy is going to have a -1 in the 2 position, and then 0. And this guy, and it will also have a minus 1. Is that 9? Yeah, do you see how it's going? I have the diagonal. I have 5 diagonals somehow. I have diagonal, the neighbor on the left, the neighbor on the right, the neighbor underneath, and the neighbor above. Across the street, you could say. So our matrix, this very important matrix, more attention has gone into how to solve this equation for that matrix than any other single specific example in numerical analysis. It's just a model problem. And what do I notice about this matrix? So now you see it's got 5 diagonals, but, and what's the big but? The big but is that those 5 diagonals it's not a band of just a band of 5, because you don't get to the one above until you've gone all the way. You see the bandwidth is big. If my matrix, if this is 1, 2 up to n, and this is 1, 2 up to n, then my matrix then how many unknowns have I got? Just let's think big now. We're in 2D, think 2D. How many unknowns have I got? N was 3 in the picture, but now you're kind of visualizing a much finer grid. How many unknowns? N squared unknowns, right? 1 to n in each direction. So we've got a matrix of size n squared, way bigger, way bigger. I mean, if n was 10, our matrix is of size 100. No, and of course, that's completely simple. The real question is when n becomes 1,000 and our matrix is of size 1,000,000. And those get solved every day. So question is how? Actually, for a 1,000,000 by 1,000,000 matrix, this fast Poisson solver that I want to describe does it great. Actually, so you can deal with a matrix of order 1,000,000 without turning a hair. Okay, now, but can we understand that matrix? So suppose n is 100, just to have us. What's the story? This matrix, then, what's the size of that matrix? Did I say 100? Or 1,000? What do you want to think really big? I guess I said 1,000, didn't I, to get up to 1,000,000. Right. Okay. So n is 1,000. So we have 1,000 by 1,000, 1,000,000 unknowns. My matrix is 1,000,000 by 1,000,000. Let me ask you this. Here's the question that I want to ask you. What's the bandwidth? How far from the main diagonal out to the last, out to that minus 1? In other words, this is really the full band of the matrix. It's got a lot of zeros inside the band, a whole bunch, maybe 990 something zeros in here and in here. And how far is it from here to here? 1,000, right? It's 1,000. So the bandwidth is 1,000, and what if I do ordinary? So now I want to begin to think, how do I solve this equation? How do I work with that matrix? And you have an idea of that matrix? It's a beautiful matrix to work with. It's very like our K matrix. It's just up to 2D. In fact, it's closely connected to our K2D will be closely connected to K, and that's what makes life possible here. But okay. Suppose I had to solve this equation. All right. So I give it to MATLAB just as a system of equations, 1,000,000 equations, 1,000,000 unknowns. So MATLAB takes a gulp, and then it tries, okay? So what will ordinary elimination? That's what backslash does. By the way, this matrix is symmetric, and you won't be surprised it's positive definite. Everything is nice about that matrix. In fact, more than I've said. Okay, what happens if I do elimination on that matrix? Okay, how long does it take? How fast is it? Well, MATLAB will take advantage, or any code will take advantage of all these zeros, right? In other words, what do I mean by take advantage? And what do I mean by elimination? You remember I'm going to subtract multiples of this row. There'll be a -1 below it on this guy, this row that has some 4s and some -1s, whatever. Elimination, I'm subtracting a multiple of this row from this row to get that -1 to be a 0, right? I'm eliminating this entry in the matrix. This is ordinary, the LU. This is ordinary LU of K2D is what I'm sort of thinking through LU of K2D. And what I'm going to conclude is that there ought to be a better way. It's such a special matrix, and it's going to be messed up by LU. And what do I mean by messed up? I mean that all these great zeros, 990-something zeros there and there, inside the band, are going to fill in. That's the message. If you want to talk about solving large linear systems, the big issue is fill in. It's a sparse matrix. That's typical. We have a local operator here, so we expect a very local sparse matrix. Large sparse matrices is what we're doing now. And the problem is that zeros here will never get touched because we don't need any elimination. They're already 0. But all this diagonal of -1s, when we do eliminations to make those 0, then some non-zeros are going to come in and fill in the zeros. So the work, how much work would elimination be, actually? We could even think about that. I haven't. Can I just give the result for how much time would elimination take? Ordinary elimination. So I have n squared rows to work on. N squared rows to work on. And then that distance was what in terms of n? The width there is n, right? It was about 1,000. So I get n numbers here, and I have to work on n numbers below. Every column, to clean up a column, I'm working with a vector of length n, and I'm subtracting it from n rows below. So cleaning up a column takes me n squared operation. The total then is n4th for elimination. And that's not acceptable, right? If n is 1,000, I'm up to 10 to the 12th. So elimination is not a good way to solve elimination in this ordering. Yeah. So can I tell you two better ways to deal with this problem? So two better ways to deal with this problem. One is, and MATLAB would have a code that would do it. One is to change from this ordering 1, 2, 3, 4, 5, 6, 7, 8, 9, change to a different ordering that had less fill-in. So that's a substantial part of scientific computing, is to change from, to reorder the unknowns, to reduce the number of wasted, of fill-in things that you have to fill in and then you have to eliminate out again. And I can get that n4th down quite a bit that way. Okay, so that's a topic of importance in scientific computing, is given a large linear system, put the rows and columns in a good order. Okay, so and that's something you hope the machine can do. The machine will have record of where are the non-zeros, and then so you run a little, you really run the program twice. You run it once without using the numbers, just the positions of non-zeros to get a good ordering so that the number of elimination steps will be way down. And then you run it with the numbers in that good order to do the elimination. So that's a topic of, one topic in this. But today's topic is using the fact that this is a square, that this matrix has a special form, that we can actually find its eigenvalues and eigenvectors, and that's what makes a fast Poisson solver. So that's the topic of the lecture and the topic of the next section in the book, and I will get started on it now and then complete it Wednesday. So I want to take this particular K2D for a square and show a different way to solve the equations that uses the fast Fourier transform. When you see a regular mesh, regular numbers, nothing varying, constant diagonals, think fast Fourier transform. The FFT has got a chance when you have matrices like this one. And I want to show you how it works. Okay. So, yeah, I want to show you the underlying idea, and then we'll see the details of the fast Fourier transform in the Fourier section. So, of course, everybody knows the third part of this course, which is coming up next week, we'll be well into it, is the Fourier part. Okay. But I can give you, because we've seen the eigenvectors and eigenvalues of K, I can do this now. Ready for the smart idea? The good way, and it only works because this is a square, because the coefficients are constant, because everything's beautiful. Here's the idea. Okay. Central idea. Signal. Okay. All right. The idea is, so I have this matrix K2D, and I'm trying to solve a system with that particular matrix. And the fantastic thing about this matrix is that I know what its eigenvalues and eigenvectors are. So let's suppose we know those. Okay, so I know K2D y equals lambda y. Y is an eigenvector. Remember, it's got n squared components. Lambda is a number. And I've got a whole lot of these, y, k, lambda, k, y, k. And I've got k going from 1 up to n squared. Okay. Now I want to use them. I want to use them to solve K2D u equal f. Let me say, it's totally amazing that I would, in fact, this is the only important example I know in scientific computing, in which I would use the eigenvalues and eigenvectors of the matrix to solve a linear system. You see, normally you think of eigenvalue problems as like, those are harder. It's more difficult to solve this problem than this one, normally, right? That's the way to think about it. But for this special matrix, we can figure out the eigenvalues and eigenvectors by pencil and paper. So we can know what these guys are. And that will give us a way to solve a linear system. So can I remember, this is now central message. What are the 3 steps that to use eigenvectors and eigenvalues in solving linear equations, in solving differential equations, in solving difference equations? They're always the same 3 steps. Can I remember what those 3 steps are? So step one. So I'm supposing that I know these guys. First of all, that's amazing to know them in advance. And the second amazing thing is that they have beautiful structure. And those facts make it possible to do something you would never expect to do. Use eigenvalues for a linear system. So here's the way to do it. 3 steps. 1, expand F as a combination of the eigenvectors. C1, Y1 up to however many we've got. We've got n squared of them. Gosh, we're loaded with eigenvectors. Okay. You remember, this is a column of size n squared. Our problem has size n squared. So it's big, 1,000,000. So I'm going to expand F in terms of the 1,000,000 eigenvectors. Okay. So that tells me the right-hand side. Now, you remember step 2 in this 1, 2, 3 process? Step 2 is the easy one, because I want to get, what am I looking for? I'm aiming for, of course, the answer I'm aiming for is K2D inverse F. Right? That's what I'm shooting for. That's my goal. That's the solution. So here I've got F in terms of the eigenvectors. Now I want to get, how do I get U in terms of the eigenvectors? Well, what's the eigenvalue for the inverse, for K2D inverse? Do you remember? It's 1 over. It's 1 over the eigenvalue, right? If this is true, then this will be true with lambda K inverse. It's simple, and I won't stop to do it, but we could come back to it. So I know how to get K2D inverse. Okay, so that's what I'm going to do. I'm going to divide, so here's the fast step. Divide CK, each of those CKs by lambda K. What do I have now? I've got C1 over lambda 1 Y1 plus Cn squared, the last guy, divided by its eigenvalue times its eigenvector. And that's the answer. Right? That's the correct answer. If this is the right-hand side, then this is the solution. Because why? Because when I multiply this solution by K2D, it multiplies every eigenvector by the eigenvalue. It cancels all the lambdas, and I get F. Do you see? I can't raise that board, and I'm sorry. Can you see it at the back? Should I write it up here again? Because everything hinges on that. That the answer U, the K2D inverse F, is the same combination that gave F, but I divide by lambda 1, C2, Y, second eigenvector over lambda 2, and so on. Because when I multiply by K2D, multiplying each Y, each eigenvector, will bring out an eigenvalue. It will cancel that, and I'll have the original F. Yeah. So do you see that those are the steps? The steps are, you have to do you could say it's a transform into eigenspace. I take my vector in physical space. It's got its n squared components at physical points. I express it in eigenspace. By that I mean it's a combination of the eigenvectors, and now the n squared physical values are n squared amplitudes or amounts of each eigenvector. That's the Fourier series idea. That's the Fourier transform idea. It just appears everywhere. Express the function in the good basis using these good functions. In these good functions, the answer is simple. I'm just dividing by lambda. Do you see that I'm just dividing by lambda, where if it was a differential equation, this is just what we did for differential equations. What did I do for differential equations? Suppose, do you mind if I just ask you? If I was solving du dt equals k2 du, starting from f, start with u of 0 as f. I just want to draw the analogy. How did we solve these equations? I expanded f in terms of the eigenvectors. And then what was step 2? If for the differential equation, I didn't divide by lambda k, what did I do? I multiplied by e to the lambda kt. You see, it's the same trick. Just get it in eigenspace. In eigenspace, it's like one tiny problem at a time. You're just following that normal mode. And here, so here, instead of dividing by lambda, I multiplied by e to the lambda t. And for powers for k2d to the 100th power, I would multiply by lambda to the 100th. Here I have k2d to the minus first power, so I'm multiplying by lambdas to the minus 1. Okay, and then the key point is that these c's can be found fast, and this summing up can be done fast. Now that's what's also very exceptional, and that's where the FFT comes in. The fast Fourier transform is a fast way to get into eigenspace and to get back when eigenspace happens to be frequency space. You see, that's the key. In other words, these y's and lambdas that I said we knew, these y's, the eigenvectors, are pure sign vectors. So that this is an expansion, is a sign transform, S-I-N-E, a pure sign transform. And that can be done fast, and it can be inverted fast. So you see what makes this fast Poisson solver work is I have to know the eigenvectors and eigenvalues, and they have to be fantastic vectors like sign vectors. Okay, so I'll give you the final picture, the details Wednesday, and then move on to finite elements.